for Theorem 3. Okay, so in this theorem, we often think of them as like a butterfly angle or something. But here we have two triangles within our circle. They don't have to be centered about the, you can even call this, say, if this was the center, they don't have to be centered or connected to the center of the circle. But basically what Theorem 3 states is that if I have two angles in the same segment, such as this angle, and I'll show you what I mean by segment now, but if I have two angles, A and B, in the same segment, then I automatically know that angle, let me find a better place to write really, angle A equals angle B. Okay. And that is regardless of how I move this angle along. If it shifted over, and I'm going to here, an angle, as long as they're on the circumference of the circle, angle A and angle B will be equal. Alright, so how do we know this and how can we prove it? Let's go forward. So I'm going to erase again quickly. And I'm going to redraw this in an interesting way. And once again, the word subtending comes in. And we'll see that soon. Erase this. We draw our circle borders in again. Alright, so from where we have it, I'm going to draw 2 points. And I'm first going to define a segment for us, because this theorem is about angles in a segment. Angles in a segment. Okay, so, and this is where one of your homework problems came from. So I'm first going to define a segment. A segment of a circle is a portion of it that is kind of demarcated by a chord that comes across. So I could say this is a segment over here. Here I just have a straight line. And notice that this line isn't the same as the diameter. If this is the center of the circle, this line isn't passing, it isn't two radiuses, so it isn't passing through the center of the circle. So it isn't a diameter, but this is a segment of the circle. And so from the segment, what I'm going to initially draw is a first point, okay? A point that is going to be, with two rays, a point that can be subtended by this line segment, okay? So subtending obviously again meant I have the one ray that gets to the one endpoint, the other ray to the other endpoint, okay? And now from our previous theorem, very similar to the one going through the diameter, I know, so I'm going to call this guy A, I know that regardless of where I move this point along this upper or along the circumference here, angle A is going to stay the same. Angle A will be equal, okay? We saw that from Theorem 1. So it seems logical then that if I have that point and being subtended by this line, so because it's subtended, angle A doesn't change, well, I could then say that, imagine me shifting along this triangle up here, moving it along the circumference until I get to a point here. Now, this point, I'm going to draw to the end point over here, another ray to it over here, and here, now, so this is the same as me having taken this point and kind of dragging it along the circumference until I get to this point, and I can call this angle B. And I can, if I'm just looking at this triangle B now, I can still see that it's being subtended by the same line, okay? And that must mean, because it's subtended still, that this angle hasn't changed. Angle A is still the same as angle B, okay? Because it's sitting on the circumference, it's subtended by a line, a segment, and so therefore I have this criteria that A equals B, angle A equals angle B. Okay, and when we often see this, it isn't as straightforward to see, but I can just erase this line. I can erase this line, or you can think of it as an arc segment, perhaps. But there you go. There is the theorem being fulfilled. QED. Cool.